Next one is we are going to see how to create a cascaded object and how to draw the S parameters for a RF object. Okay, so this is going to be completely into high frequency because we are going to plot the S parameters. So you know that however high frequency you are going to operate, you cannot measure voltage and current. So I cannot draw time versus voltage or time versus current graphs. What I have is frequency versus S parameters graph only I have in my hand. That is only going to be meaningful for the analysis. Okay, so see here, I am going to see this is the cascade circuit I am going to create. First circuit, second circuit, third circuit. First circuit is transmission line, second circuit is an amplifier, and third circuit is a transmission line. So see here, I am just creating three objects. First circuit transmission line, second circuit amplifier, and I'm reading the amplifier parameters. And third circuit is transmission line, and again the parameters are given. Line length is given 0.025, and the phase velocity is 2e8, 2 into 10 power 8 meters per second. So now I'll just run this section. So it is run. So I'm getting the properties of first circuit. See here, the properties are coming. Velocity Z0 is 50, frequency is 1 gigahertz. Everything is designed. Second circuit amplifier, you see, all the amplifier parameters are coming. Third circuit, you see, again, whatever we have given, it is taken everything. Now, I am going to use the methods. I am going to use the methods of third circuit to list the objects. Okay. So now, for the first circuit, I am fixing the length. I am finding the default length. So use the default length method, and I'm going to assign that to the new length. So I'm getting the default length and I'm updating the new length. Okay, so that is what is done here. So whatever is the default length, I'm replacing it by 0.01. Okay, now I'm plotting the Smith chart. Smith chart of second circuit alone. Second circuit is going to be amplifier. The amplifier alone, I'm plotting the Smith chart. And you see the frequency is varying from 1 to 2.9 gigahertz. And S parameters 1122, which means that it is a 2 by 2 matrix. So I plot S11 and 22. I plot only S11 and 22. 11 is the input reflection coefficient. 22 is the output reflection coefficient. If you give 12 and 21, you will get two more graphs here for S12 and S21. Now I am plotting the second circuit. What is the output, input-output data? You see that as the input is increasing, the output was also increasing and then becoming constant. So till this point, I can say my amplifier is linear. After this, it goes into saturation. So you know that in electronics, all the components have to be operated only in the linear region. If you don't operate the components in linear region, the output will become non-linear. But the sad thing is all the components which you encounter in the real world are highly non-linear. Then how can we model everything using linear models? So that in all the non-linear also, you will have a portion of the graph which is going to be linear. So I'm going to fix that as my reference and I'm going to model my circle. In this circuit, this graph is not completely linear, correct? So it is linear till this point and then it is constantly saturating. So till this point, I can assume the circuit to be linear and I can operate the circuit only from this point to this point. Above this point, my circuit becomes non-linear. Okay, this is the input-output graph of my amplifier.